Tonight I want to take you somewhere at the very boundary between what we know and what we can barely imagine. A place where the familiar rules of reality begin to bend and flow like honey, where time itself stretches and yawns, and where light, that most fundamental messenger of the universe, meets its most extraordinary challenge. Tonight, we're going to explore what happens to light at the exact edge of a black hole, at that mysterious threshold we call the event horizon. As you settle in wherever you are, perhaps tucked under warm blankets, maybe with the soft glow of your screen the only light in the room, I wonder where in the world you might be listening from. Is it late at night where you are, or perhaps early morning, that quiet time when the world feels still and possibilities seem endless? Whatever corner of our small planet you're resting in, whatever time zone cradles you right now, you've found your way here to contemplate one of the universe's most profound mysteries with me. And if these gentle explorations of the cosmos bring you peace, if they help you drift into restful sleep while your mind wanders through the stars, perhaps you'd like to join me on more of these journeys. A quiet like, a gentle subscribe. These small gestures help us continue our peaceful travels through the wonders of space and time together. It's a question that might sound strange at first, something you could easily dismiss as the stuff of science fiction. But the more we look at it, the more quietly intriguing it becomes. What happens to light, that thing we take for granted every day, that illuminates our mornings and carries the images of distant stars, when it encounters the ultimate cosmic trap? What if this question about light meeting the edge of a black hole was not just a dry equation in a physics textbook, but a quiet doorway into understanding how the universe really works at its most extreme boundaries? We begin our journey tonight by stepping back, far back, to consider the vastness of space that surrounds us. Out there, in the cosmic darkness that stretches between the stars, light travels freely. It races across the void at that ultimate speed limit of the universe, 186,282 miles per second, a velocity so tremendous that it could circle our entire Earth 7.5 times in the span of a single heartbeat. This light, these photons that have been streaming through space for millions, sometimes billions of years, carry with them the stories of the cosmos. They bring us the gentle glow of distant galaxies, the fierce brightness of newborn stars, the soft radiance of planetary nebulae where dying suns have breathed their last gasps into the darkness. And yet, scattered throughout this vast cosmic ocean, there are places where even light must surrender, places where gravity has become so intense, so overwhelmingly powerful, that space itself has been twisted into a one-way street from which nothing can return. These are the black holes, perhaps the most mysterious and awe-inspiring objects in all of existence. They are not holes in the traditional sense, not empty spaces or voids, but rather regions where matter has been compressed to such an extreme degree that they've torn a kind of wound in the fabric of space-time itself. To understand what happens to light at the edge of a black hole, we must first understand something about the nature of both light and gravity. You see, light has always been our cosmic messenger. Every star you've ever seen, every galaxy captured by our most powerful telescopes, every sunset that has painted the sky in shades of gold and crimson, all of these experiences come to us courtesy of light's faithful journey across space and time. Light seems so free, so unstoppable. It passes through the vacuum of space without slowing, without tiring, maintaining its incredible speed no matter how far it travels. But gravity is the silent architect of the universe. It's the force that gathered the first wisps of hydrogen gas after the Big Bang and compressed them until they ignited into the first stars. It's what keeps our feet firmly planted on Earth, what guides the moon in its monthly dance around our planet, what orchestrates the spiral arms of galaxies in their slow, centuries-long rotations. And in black holes, gravity reaches its ultimate expression. Imagine, if you will, space as a vast, flexible fabric, perhaps like a sheet of silk stretched gently across a frame. Every object with mass creates a little dip in this fabric, a small depression. The Earth creates a modest dip, which is why objects fall toward it. The Sun creates a deeper depression, which is why planets orbit around it. But a black hole creates something else entirely. It creates a depression so deep, so profound, that at a certain point the fabric doesn't just dip, it effectively tears, creating a region from which nothing can climb back out. This boundary, this point of no return, is what we call the event horizon. The name itself carries a certain poetry, doesn't it? An event horizon, the horizon beyond which no events can ever be witnessed by the outside universe. It's not a physical surface that you could touch or feel. There's no wall, no barrier in the traditional sense. Instead, it's more like an invisible boundary drawn by the laws of physics themselves, a line that says, beyond this point, the rules change forever. As we contemplate this boundary tonight, as we let our minds drift toward these cosmic extremes, we find ourselves at the heart of one of physics' most profound questions. What exactly happens when light, that speediest of all things, that carrier of information and energy, encounters this ultimate boundary? The answer, as we'll discover together, reveals something deep and beautiful about the nature of space, time, and reality itself. At first, it feels like it shouldn't work this way. Light has no mass, after all. We learned in school that gravity acts on objects with mass. That's why a feather and a hammer would fall at the same rate on the moon, where there's no air resistance. But light? Light is pure energy, electromagnetic radiation rippling through space. How can gravity, which we think of as pulling on massive objects, affect something that has no mass at all? And yet, when we look closer, something else begins to appear. Einstein, in his beautiful theory of general relativity, showed us that gravity isn't really a force pulling on objects. Instead, it's the curvature of space-time itself. Mass and energy bend the fabric of space and time, and objects, including light, simply follow the curved path through this warped landscape. It's like rolling a marble across a stretched rubber sheet that has a heavy ball pressing down in the middle. The marble doesn't get pulled by the ball, it simply follows the curved surface. So light, racing through space at its incredible speed, finds its path beginning to curve as it approaches a black hole. At first, the curvature is subtle, barely noticeable. A beam of light passing far from the black hole might have its path bent by just a tiny fraction of a degree. We see this effect with our own sun. During a solar eclipse, stars that should be hidden behind the sun become visible because their light has been bent around it. Einstein predicted this, and when it was observed in 1919, it made headlines around the world. But as light ventures closer to a black hole, the curvature becomes more dramatic. The path of light begins to bend more severely, curving around the black hole like water swirling near a drain. There's a special distance from the black hole, about 1.5 times the radius of the event horizon, where something remarkable happens. At this distance, called the photon sphere, light can actually orbit the black hole. Imagine that, photons racing around and around in perfect circles, trapped in an endless loop by the extreme curvature of space. If you could somehow stand at this photon sphere and look straight ahead, the curvature of space would be so extreme that light from the back of your head would travel all the way around the black hole and reach your eyes. You would see the back of your own head, an infinite number of times, each image slightly older than the last, creating an endless tunnel of self-reflection, stretching both forward and backward in time. Of course, no one could actually stand there. The tidal forces would tear any physical object apart. But light itself can exist in this strange orbital dance, at least temporarily. Now, as we follow light even closer to the event horizon, something even more extraordinary begins to happen. Time itself starts to behave strangely. You see, Einstein showed us that gravity doesn't just bend space, it also affects the flow of time. The stronger the gravitational field, the slower time passes relative to the outside universe. Near the event horizon of a black hole, this effect becomes extreme. Imagine we're watching a brave photon, a single particle of light, approaching the event horizon from a safe distance. As it gets closer and closer to that invisible boundary, something peculiar happens from our perspective as outside observers. The light appears to slow down. But wait, how can light slow down? Doesn't light always travel at the same speed? Here's where the mystery deepens. The light isn't actually slowing down in its own reference frame. If you could somehow ride along with that photon, you would still measure yourself traveling at the speed of light. But from our perspective, watching from outside, time itself is dilating near the event horizon. Each second that passes for the light near the horizon corresponds to longer and longer periods of time for us watching from afar. As the light gets infinitesimally close to the event horizon, This time, dilation approaches infinity. From our outside perspective, we would see the light's approach to the horizon slow more and more, its wavelength stretching out, becoming redder and redder, dimmer and dimmer, until it fades from view entirely. We would never actually see it cross the event horizon. It would appear to freeze at the boundary, its last photons trickling toward us ever more slowly, carrying information from a moment that, from our perspective, never quite completes. But from the light's own perspective, if a photon could experience anything, it would notice nothing special as it crosses the event horizon. It would simply continue inward, following the curved space-time, unable to turn back not because of any physical barrier, but because space itself has been curved so severely that every possible path, forward, backward, sideways, all lead deeper into the black hole. The future itself has been bent to point inevitably toward the center. Scientists have observed these effects, though not directly at black hole event horizons. Those are still too far away and too extreme for our current instruments to resolve in such detail. But we've seen the principle at work. GPS satellites orbiting Earth have to account for time dilation. Their clocks run slightly faster than clocks on Earth's surface, because they are in a weaker gravitational field. Without correcting for this relativistic effect, GPS would accumulate errors of about 10 kilometers per day. We've also observed light being bent by massive objects throughout the universe. Galaxy clusters, containing trillions of times the mass of our Sun, act as gravitational lenses, bending and magnifying the light from more distant galaxies behind them. Sometimes this creates multiple images of the same galaxy, or stretches them into beautiful arcs of light called Einstein rings. These observations confirm that light indeed follows the curvature of space-time, just as Einstein predicted. When it comes to black holes specifically, we have increasingly dramatic evidence. The Event Horizon Telescope, a network of radio telescopes spanning the globe, has actually photographed the shadow of supermassive black holes, first in the galaxy M87, then in our own Milky Way's center. What we see in these images is not the black hole itself, of course. Nothing can escape from within the event horizon to create an image. Instead, we see the glowing disk of superheated matter spiraling toward the black hole, and in the center, a dark shadow roughly 2.5 times the size of the event horizon. This shadow is created by the photon sphere and the region within it, where light cannot escape to reach our telescopes. The data reveals something profound. We can see matter heating up to millions of degrees as it spirals inward, glowing brilliantly in X-rays and radio waves. We can trace the motion of stars orbiting invisible massive objects at velocities that reveal the enormous gravitational pull they're experiencing. The star S2, for instance, orbits the supermassive black hole at the center of our galaxy at speeds exceeding 7,000 kilometers per second at its closest approach. These observations match perfectly with what general relativity predicts should happen near such extreme gravitational fields. Scientists have also detected gravitational waves, ripples in space-time itself, from merging black holes billions of light-years away. When two black holes spiral into each other and merge, they shake the very fabric of space and time, sending out waves that stretch and compress space as they pass through. The LIGO and Virgo detectors have measured these passing waves, distortions so tiny that they change the length of the detector arms by less than 1,000th of the width of a proton. Yet from these minute measurements, we can read the story of black holes colliding, their event horizons merging into one, happening so far away that the light from their host galaxies has been traveling toward us since before our solar system was born. Perhaps the universe prefers this arrangement, these cosmic boundaries that mark the limits of observation, the edges of what can be known from outside. Maybe there is a deeper pattern we do not yet see, a reason why nature draws these veils across certain regions of space. Some scientists wonder if the event horizon serves a crucial role in preserving the consistency of physical laws, preventing paradoxes that might arise if we could observe matter in the extreme conditions near a singularity. One intriguing possibility is that the event horizon protects the outside universe from the breakdown of physics that might occur at the black hole's center. According to general relativity, at the very center of a black hole lies a singularity, a point where density becomes infinite and the known laws of physics cease to function. The event horizon ensures that this breakdown, if it truly occurs, remains forever hidden from external observers. This is called cosmic censorship, and while it hasn't been proven, it seems to be how nature arranges things. There are also tantalizing hints that the event horizon might not be as simple as we once thought. Stephen Hawking showed that quantum effects near the event horizon should cause black holes to slowly evaporate, emitting what we now call Hawking radiation. This process is so slow for stellar mass black holes that they would take longer than the current age of the universe to evaporate significantly. But it suggests that the event horizon is not just a geometric boundary, but a place where quantum mechanics and general relativity meet in ways we're still trying to understand. If this is true, what does it say about our place in the universe? We live in a cosmos where light, the very thing that brings us information, that connects us to the stars, that allows us to see and be seen, can be trapped forever by gravity. We exist in a reality where there are regions we can never explore, boundaries we can never cross and return from, knowledge that must forever remain hidden from us. Yet perhaps this limitation is also a gift. The existence of event horizons means we live in a universe with genuine mysteries, with boundaries that preserve wonder. No matter how advanced our technology becomes, no matter how sophisticated our theories, there will always be regions of space that remain beyond our direct observation, forcing us to be creative, to theorize, to imagine. If such things exist, these borders where light itself must surrender to gravity, what might that mean for how we understand existence? It suggests that the universe has built-in limits to knowledge, that there are questions whose answers lie forever beyond any possible observation. It reminds us that we are finite beings in an infinite cosmos, able to understand tremendous things, yet always bounded by horizons we cannot cross. Even in our smallness, we reflect these same laws. The atoms in our bodies obey the same quantum mechanics that governs behavior near black holes. The space we occupy curves ever so slightly due to our tiny mass, just as space curves dramatically near an event horizon. We are part of this vast pattern, made of the same stuff, governed by the same rules, participants in the same cosmic dance that plays out at the edges of black holes. We come back, again and again, to the same quiet question. What happens to light at the exact edge of a black hole? Perhaps it has been there all along, whispering in the background of our contemplation. This idea that boundaries exist not just in space, but in knowledge itself. We've seen how the everyday picture we might have, light simply falling into a hole, gives way to something far stranger and more beautiful. We've discovered the scientific puzzle of how massless light can be affected by gravity, and we've found the surprising resolution in the curvature of space-time itself. Yet mysteries remain, deeper questions about what happens to information that falls past the event horizon, about how quantum mechanics and gravity truly unite at these extreme boundaries. Let's imagine ourselves there for a moment, floating near a black hole's event horizon, safely, impossibly, in our imagination only. Below us, if below has any meaning here, stretches that invisible boundary. We wouldn't see a surface, wouldn't observe a wall. Instead, we might notice how stars in the distance seem to cluster more densely in one direction, how their light seems bluer, more energetic as we look away from the black hole. Looking toward it, we might see a growing darkness, a region where fewer and fewer stars are visible, until there's simply nothing. Not blackness in the ordinary sense, but an absence of light, an absence of information, an absence of possibility for any signal to reach us from within. If we released a beam of light toward the event horizon, we would see it race away from us at that constant ultimate speed. But as we watched, something strange would occur. The light would seem to slow as it approached the horizon, not because it's actually decelerating, but because time itself is stretching near that boundary. The wavelength would stretch too, shifting toward the red end of the spectrum, then into infrared, then into radio waves, then into wavelengths so long they would take years, centuries, millennia to complete a single oscillation. From our perspective, the light would never quite reach the horizon, instead fading gradually from our ability to detect it, carrying its last information in ever slower whispers. Meanwhile, all around this drama of light and time, space would continue its patient work. Other photons would spiral past us, following the curved paths that Einstein's equations predict. Some would orbit temporarily in that remarkable photon sphere, racing around the black hole at the speed of light, creating a bright ring of trapped radiation. Others would skim past and escape, carrying their information back out to the universe, but bearing the mark of their close encounter in their shifted wavelengths and altered paths. In another quiet corner of research, scientists are discovering even more subtle effects. They've found that rotating black holes, and most black holes in the universe do rotate, create an additional region just outside the event horizon called the ergosphere. In this region, space itself is dragged around by the black hole's rotation. Nothing can remain stationary here. Everything must rotate with the black hole. Light entering the ergosphere finds its path twisted not just by gravity, but by this rotation of space itself. Somewhere in a lab, late at night, researchers pore over data from telescopes, tracing the paths of light around distant black holes. They see jets of material being ejected at nearly the speed of light from the regions near supermassive black holes, powered by magnetic fields so strong they can accelerate particles to tremendous energies. They observe light from stars being stretched and compressed as they orbit black holes, their spectral lines shifting back and forth in a cosmic dance that reveals the invisible partner's mass. Telescopes collect pale light that has traveled for ages, light that has skirted the edges of black holes billions of light years away. In this ancient light, scientists can read stories of cosmic catastrophe and creation. They see quasars, supermassive black holes feeding on surrounding matter, shining with the brightness of entire galaxies. They observe tidal disruption events, where stars venture too close to black holes and are torn apart, their matter spiraling inward in a brilliant accretion disk, their light performing a final glorious display before vanishing forever beyond the event horizon. Scientists ponder possibilities that stretch the imagination. What if black holes aren't perfectly black? Some researchers have wondered whether information that falls into a black hole might somehow be preserved on the event horizon itself, encoded in microscopic fluctuations of the horizon's area. This is the holographic principle, the idea that all the information within a region of space can be described by information on the boundary of that region. It is possible, though not yet proven, that the event horizon acts like a cosmic hard drive, storing the information of everything that has ever fallen past it in a scrambled but theoretically recoverable form. There are even more exotic possibilities being explored. Some scientists wonder if black holes might connect to other regions of space-time through wormholes, though the mathematics suggests such connections would be unstable and collapse faster than light could traverse them. Others investigate whether the interiors of black holes might spawn new universes, regions of space-time that inflate and evolve independently, forever disconnected from our own cosmos. These ideas remain highly speculative, but they illustrate how black holes push us to the very boundaries of theoretical physics. What does it mean that our minds can imagine such things? Here we are, collections of atoms organized in just the right way to contemplate the universe that created us. We can describe mathematically what happens to light at the edge of a black hole, even though we can never go there ourselves. We can calculate the curvature of space-time in regions so extreme that atoms themselves would be torn apart. Yet we do this with brains made of those very atoms, sitting safely on a small planet orbiting an ordinary star. What does it say about us? That we can describe a universe we barely see. We've detected black holes through their influence on nearby stars, through the radiation emitted by matter falling toward them, through the gravitational waves they create when they merge. We've never seen an event horizon directly. We can't, by definition, yet we can predict with extraordinary precision what should happen there. Our mathematics, developed from observing falling apples and orbiting planets, somehow extends to describe the most extreme environments in the universe. There's something profound in this connection between the human mind and the cosmic order. When you take a breath, the atoms entering your lungs follow the same quantum mechanical rules that govern matter near a black hole's event horizon. When you see light from a lamp or a star, you're observing the same electromagnetic radiation that struggles against gravity at the photon sphere. The passage of time that you experience, the steady tick of seconds and minutes, is the same phenomenon that slows to a crawl near the event horizon. In your everyday moments, watching a sunset, feeling the warmth of sunlight on your skin, seeing your reflection in still water, you're experiencing the same light that elsewhere in the universe is being captured by black holes, twisted into spirals, stretched into invisibility. The light that illuminates your morning coffee has cousins racing through space that will, in billions of years, encounter event horizons and cross boundaries from which they can never return. No matter how strange the universe becomes in our equations, here you are, breathing, resting, held by gravity, held by the quiet laws that never stop working. The same physics that creates the dramatic environment near a black hole also creates the gentle conditions that allow you to exist. The same space-time that can curve so severely that it traps light forever also curves just slightly around Earth, just enough to hold an atmosphere, to keep water liquid, to allow life to flourish. Perhaps the questions themselves are enough for tonight. As we've journeyed together toward the edge of a black hole, we've encountered mysteries within mysteries. We've seen how light, that most fundamental aspect of our daily experience, behaves in ways that challenge our intuition when it meets extreme gravity. We've discovered that the event horizon is not a place, but a point of no return, not a wall, but a warping of space-time so severe that all paths lead inward. Maybe it is enough just to feel the wonder of not fully knowing. We understand so much, how black holes form, how they grow, how they bend light and space and time. Yet fundamental questions remain. What happens to information that crosses the event horizon? How does quantum mechanics truly behave in such extreme gravitational fields? Are there really singularities at the centers of black holes? Or does some new physics intervene before densities become infinite? The universe continues its quiet work whether we understand it or not. Right now, as you rest and listen, light is approaching a vent. Horizons throughout the cosmos. Photons that have traveled for millions of years are taking their final journeys, crossing boundaries from which they'll never return. Stars are orbiting black holes, their light stretched and compressed by tidal forces. Accretion disks are glowing with fierce radiation as matter spirals inward, converting gravitational energy into light in one final burst of brilliance before disappearing forever. These phenomena we've discussed tonight keep unfolding moment by moment throughout the universe. In distant galaxies, supermassive black holes that weigh billions of times more than our Sun are bending light into Einstein rings, creating cosmic mirages that reveal the universe's hidden structure. In our own galaxy, stellar mass black holes drift silently through space, invisible except for their gravitational influence, occasionally revealing themselves when they capture a passing star or accumulate a disk of glowing gas. Questions matter more than answers in our contemplation tonight. The question of what happens to light at the edge of a black hole has led us through a journey of space-time curvature, of time dilation, of event horizons and photon spheres. It has shown us that the universe operates by rules that seem strange and counterintuitive, yet are beautifully consistent. It has revealed that there are boundaries in nature, not just in space, but in knowledge itself. It is beautiful that we live in a universe that we can keep wondering about. Every question we answer reveals new questions. Every mystery we solve opens doors to deeper mysteries. The event horizon, that boundary where light itself must surrender to gravity, reminds us that the universe will always hold secrets, will always maintain some regions beyond our reach, will always preserve a sense of wonder for those who seek to understand it. In the silence between atoms, in the spaces between molecules that make up your body, the same quantum fields fluctuate that create Hawking radiation at event horizons. In the hush between stars, light races through the void, most of it traveling freely forever, but some destined to encounter the ultimate boundaries of black holes. Somewhere, the phenomenon we've talked about tonight is still unfolding. Light is approaching event horizons, time is dilating, space is curving, and the universe is writing its story in paths of light that sometimes end in darkness. We return gently to the exact question that brought us here tonight. What happens to light at the exact edge of a black hole? We've learned that it's not a simple answer. From one perspective, light appears to slow and freeze at the event horizon, its final photons redshifting into invisibility. From another perspective, the light crosses the horizon noticing nothing special, simply following the curved paths of space-time into a region from which it cannot return. Both perspectives are correct, both are incomplete, and both remind us that reality is far stranger and more beautiful than our everyday experience might suggest. The universe continues its quiet work. Black holes grow as matter falls past their event horizons. Light continues its cosmic journeys, most of it traveling freely through space, bringing us images of distant galaxies and nearby stars. But some light inevitably encounters these cosmic boundaries. Some photons, after travelling for billions of years across the cosmos, meet their end not in the sensor of a telescope or the eye of an observer, but in the inexorable pull of an event horizon. And as you drift into sleep, you remain part of this quiet universe, wrapped in its laws, carried by its mysteries. The same gravity that holds you gently to Earth creates the extreme conditions at black hole event horizons. The same light that perhaps dimly illuminates your room has cousins racing through space, some free, some trapped, some balanced perfectly on the edge between escape and capture. You're made of atoms forged in stars, atoms that themselves once existed in regions of space where light struggled against gravity, where matter and energy danced at the boundaries between the known and unknowable. Tonight, as consciousness fades into dreams, you rest within the same cosmos where light meets its ultimate boundaries at the edges of black holes, where space and time curve into mysteries we're only beginning to understand, where the universe keeps its deepest secrets hidden behind veils of infinite time dilation, gently, peacefully, forever beyond the event horizons that drift silently through the cosmic night. End.